Shri Gurubhyo Namaha. Welcome to our online learning initiative Ekalaiva.
Today, we are going to discuss Lenz law and conservation of energy. In 1834, German physicist Heinrich Lenz deduced a rule known as Lenz law, which gives the polarity of the induced EMF. According to Lenz law, the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Now, let us recall Faraday's law of electromagnetic induction, what we discussed in the previous topic. According to Faraday's law, the magnitude of the induced EMF, so the magnitude of the induced EMF is equal to minus d phi b bar dt. So the time rate of change of magnetic flux. Here, what is the significance of this negative sign? Actually, this negative sign which represents this effect. So in order to understand this Lenz law, let us consider north pole of a bar magnet. So now let us assume a bar magnet. This is a north pole of the magnet. Is being pushed towards the closed coil. So now let us assume a coil which is present here. So we are going to push the north pole of the magnet towards the coil. As the north pole of the bar magnet moves towards the coil, the magnetic flux through the coil increases. Hence, current is induced in the coil in such a direction that it opposes the increase in flux. This is possible only if the current in the coil is in a counterclockwise direction with respect to an observer situated on the side of the magnet. So what is the direction of the induced current? So this is the direction of the induced current. So this is the direction of the induced current. So I can also draw here, children. And here one thing we have to know. The magnetic moment associated with this current has north polarity towards the north pole of the approaching magnet. Similarly, if the north pole of the magnet is being withdrawn from the coil, what will happen? Let's see now. So this is the bar magnet. This is the north pole of the bar magnet. And again, we are going to consider a coil which is present here. Now we are going to bring the north pole of the magnet away from the coil. So now let's see what will be the direction of the induced current. If the north pole of the magnet is being withdrawn from the coil, the magnetic flux through the coil will decrease. To counter this decrease in magnetic flux, the induced current in the coil flows in clockwise direction. So, what is the direction of the induced current? The induced current will flow in a clockwise direction. So the decrease in magnetic flux, the induced current in the coil flows in clockwise direction and its south pole faces the receding north pole of the bar magnet. This would result in an attractive force which opposes the motion of the magnet and the corresponding decrease in flux. Now let's see what will happen if an open circuit is used in the place of a closed loop. Even in this case, an EMF is induced across the open ends of the circuit. The direction of the induced EMF can be found with the help of Lenz's law. Now we are going to see an important fact here. Suppose that the induced current was in the direction opposite to the one what we depicted here. In that case, the south pole due to the induced current will face the approaching north pole of the magnet. So, here you have a north pole of the magnet, and when you bring the bar magnet, north pole of the magnet towards the coil, this face which will act like a north pole. Instead of north pole, if it is the south pole, what will happen? The south pole due to the induced current will face the approaching north pole of the magnet. Then the bar magnet will attracted towards the coil at an ever-increasing acceleration. A gentle push on the magnet will initiate the process, and its velocity and hence kinetic energy will continuously increase without expending any energy. But this violates the law of conservation of energy, and hence it cannot happen. Now once again, here we can see that the bar magnet experiences a repulsive force due to the induced current. Therefore, a person has to do work in moving the magnet. Now we'll have one doubt. Where will the energy spent by the person go? Actually, this energy is dissipated by Joule's heating produced by the induced current. So now once again, I'll repeat Lenz's law. According to Lenz's law, the polarity of induced EMF is such that it tends to produce a current which opposes the change in magnetic flux that produced it. Either it may be increasing flux or decreasing flux. Always the polarity of the induced EMF is such that it tends to produce a current. That is, the direction of the induced current always opposes the change in magnetic flux that produced it. Hope all of you understood this Lenz law, and we can say very well that Lenz law is in accordance with conservation of energy. Thank you, students.